Good. Next. Okay.
Okay, shall we get started? Okay, yeah. Hi, everyone. My name is Yuan, and I'm a co-founder of XCamp. I'm leading teaching and technology. And today, we are very happy to have our beloved teacher, Max, to talk about Gold level live solution of the December USACO competition. And Max is the ICPC World finalist, and also he has been teaching at XCamp for a long time. He's the ICPC World finalist, and he's very good at explaining very complex concepts and algorithms. To give a sense of Max class teaching quality, on the right side is a list of scores. These are the students. Sorry, these are the scores of the students in his class who got these scores in the December Gold level competition. I think majority of the class will pass Gold this time. Hopefully, it's not 800 this time. So let's go to the next page. Yeah, so then I will hand over to Max to talk about the Gold level problem tutorials. And yeah, Max, it's all yours now.
All right. Thank you, Yuan. Yep, so I'll just go ahead and jump straight into the problems. So this table here shows a brief overview of some of the topics that might be kind of used for these problems and what classes might learn them in. But let's just go ahead and jump into the solutions. So the first problem was called flight routes, and I'm going to go ahead and jump over to my whiteboard to explain. So what the problem asks is it gives us essentially a graph of these different essentially it gives a graph of n vertices. Say n is less than or equal to 750. And basically what they give us is they give us a matrix. The problem gives us a matrix. I'll say, or for every pair ij.
Just to sorry to interrupt. You probably want to show the whiteboard.
Oh,
Looks
sorry.
like
Yes. Let me share. Yeah. So everyone can see that? Yeah. Yeah. So it gives us, let's see, it gives us a matrix of I through J. And what it tells us is that, and it gives us the parity. We are given the parity of the number of paths from I to J. So parity is like even or odd, right? So that's what this is a parity. When I say parity, I mean even or odd. And now our task is we want to determine the total number of edges. We want to count the total number of edges, like direct edges in this graph. And everything was with I is less than J. So yeah. So how should we approach this problem? Well, when we look at this condition of parity, and we try to analyze the number of paths, let's say we fix a pair ij, then a path from I to J, it can be a direct path like I going to J, or it can go through some intermediate vertices. So it might go to some intermediate vertex K, K1, it might go to some intermediate vertex K2, and so on and so forth, and eventually it reaches J, right? That is the other possibility. And so let's focus. So this kind of motivates us to kind of maybe look at first maybe let's first look at like a simple case. Let's say I and I plus 1, the immediate pair. Because this graph is only has edges from I to J with I less than J. So if we're considering paths between I to I plus 1, there can't be the only possible path is like directly from I to I plus 1. There's no possible because there is no intermediate vertex that this could possibly go through. And you're not allowed to go like backwards and then back over here. That's not allowed per the constraints of the problem. So this kind of motivates us to start looking at first like the close ones, like I to I plus 1, because for those, if the parity is 1, we instantly know that it has to be an edge, right? Because if the parity something like parity equals 1, That means that implies there's an edge, and parity equals 0, there would be no edge for a simple case like this. And then if we figured out all the distance 1 pairs first, we figured out like I to I plus 1. Now next it makes sense to look at like I to I plus 2. And then from I to I plus 2, it's either like from I to I plus 2, we have like either like I directly to I plus 2, or we have like I through some intermediate vertex, say I plus 1, and then to I plus 2. But with the intermediate case, these are just like these are kind of like the previous case that we just mentioned, right? Like I to I plus 1, I plus 1, I plus 2. These are distance 1 cases, which you've already computed before. And so in general, this is starting to look like some sort of dynamic programming, in particular a range dynamic programming. And so let's analyze this now in full. So in total, suppose we have for any ij, I'm going to process these in increasing order of j minus I. What I'm going to do is essentially from I to j, we're going to first consider the case where there is an intermediate vertex. So in that case, we're going to iterate on k. So we're going to go ahead and iterate on k. And to avoid overcounting, we're going to assume that the k is the second vertex on the path. And so now, if there's an edge, from let's say from I to k, then we have the parity. Then the parity of the number of paths from k to j will all contribute to the total parity of the parity of k to j will contribute to the total parity of the paths from I to j, right? So from a counting perspective, we're basically trying to count all the intermediate paths or all the paths that go from I to j through some intermediate vertex k, where k is the second vertex on that path. And so if there's an edge from I to k, then we can take all the paths from k to j, and that all contributes to the parity. And so basically, we take for every single k where the edge exists, we take all the parity of kj, we XOR them all together because parity basically flips. And then at the end, if the total we end up with, if the total parity we end up with is not the same as like the input matrix that we got, the input matrix ij, that implies that there needs to be one more path, or we need one more. That implies that we also need a path from I to j directly without any intermediate vertices. So if this whole pair does not match, that implies that we also need an edge from I to j. So in total, we just we basically compute this for all the pairs ij in increasing order of j minus I, increasing order of j minus I, because by doing it that way, all the previous like the internal ranges like I to k and k to j will already be computed, and then we simply check. And for this, by doing this, we're able to determine for each pair ij there should be an edge between them, and this entire algorithm will work in. Let's see. So there are two for loops on I and j, and then a third for loop on k, each up to n. So this is an O of n cubed algorithm. And we remember that n was 750, so 750 cubed. That is a bit much, but we can divide this by roughly by 6, because if you think about all the triplets that we iterate over, we only iterate over I, which is less than k, which is less than j. So you can kind of divide by a factor of 6 for the amount of iteration that we do, because each triplet is only counted once and not like not like each permutation. So this will run fast enough. All right. So that is the first problem. Like I said, I can take any questions before I move on to the second one. Cool. All right, let's move to the second problem then. The second problem, so the second problem was, let's see, the second problem was named minimum longest path, and the problem basically gives us a DAG. It tells us that it gives us a DAG, so something like this, but a directed graph where some edges point to other edges, but importantly, there are no directed cycles. Each edge has some label. So each edge has some label. There are labels on the edges. And we would like to compute, what do we want to compute? We want to compute for each vertex, we want to compute two quantities. The first thing we want to compute is just the length of the longest path. The length, when I say length, I mean the number of edges. So the labels are not the total length of the labels, but like the number of edges. So the length of the longest path from this vertex. But then also, we don't just want the longest path, we want the sum of the labels of the lexicographically minimum longest path. And when I say lexicographically minimum, what we're going to do is like, there might be multiple longest paths coming from a single vertex. So we're going to consider all of them. For each one, we're going to consider all the labels on that path in order. And then we're going to pick the one that has the lexicographically smallest like array of labels. So to give a quick example, the sequence of labels 2, 4, and 5 is considered lexicographically smaller than 2, 10, and 3 because the first characters match, but then the second character 4 is less than 10, so we stop the comparison there. So you basically compare them like strings. That's the definition of lexicographically smallest. Okay, so how can we approach this problem? Oh, and the bounds, the constraints, I believe, are, let's see, n and m are up to, for constraints, it's just n less than or equal to 2 times 10 to the 5, and m less than or equal to 4 times 10 to the 5. Okay, so the first thing we could do, computing this first quantity is a relatively standard problem. This is a dynamic programming on DAG, and it's kind of like almost like one of like the introductory examples for this concept. You basically let so on a directed acyclic graph, there is an imposed order that you can do dynamic programming on. You basically just like do dynamic programming in a topological order. So like this one depends on this, and then this one depends on these, and then this one can be computed based on once this was computed, and this one can be computed once both of these are computed. And because there are no cycles, there's always like a valid topological order that we can process these states in. And then we just compute a dynamic programming where it's something like dp of u is equal to 1 plus or the maximum over all v that are adjacent to u of dp of v plus 1, where dp of u denotes the length of the longest path starting from u and going some amount, right? So this recurrence is basically, we're taking each vertex, we're considering each of the choices of where to go next, and we're taking the longest path from that point. So that's pretty standard. The second part is the non-standard part. So we want the sum of the labels, the lexicographical minimum longest path. And we need this for each vertex. So if you think about this for a bit, you will realize that there might be a weird cases where, so if you have a case, like for example, this vertex has 2 outgoing edges, 2 other vertices, and there are paths. Let's say both of these are optimal. So like from both of these, there are paths of optimal length. So you can choose to go through either of these. And one of these has label 3 and one of these has label 4. Well, then we're done because the one through label 3 is going to be lexicographically smaller. So of course we should take that one. But suppose they have the same label, they both have 3. Well, then just looking at this edge is not sufficient. So we have to like kind of look like one step further, right? So maybe now we look at the next one. Maybe this one has like some outgoing edges. this one has outgoing edges as well. And maybe let's say these labels are like 4, 10, 7, and this one has 3 and 4. So in this case, clearly the 3 and the 3 is optimal, so we just stop, and this is the optimal path. But like, let's say this 3 wasn't here, and this was instead a 5, then now we have both this 4 and this 4 are possible. And so we kind of have to keep looking. And so in general, like this might blow up to like an n squared procedure if we keep like going down and comparing the paths until we get one that is better than the other. So we can't compare the entire sequence. That is not really feasible. So we need some sort of way to like succinctly represent the information of which path is lexicographically smaller than the other one without like going down the entire sequence. And so you might try to come up with some heuristics that don't work. For example, you might think like, okay, I just compare the minimum sum instead. That isn't correct, although that passes an alarming number of test cases. But something that does actually work is to consider ranks. So here's the idea. For anything with a DP value of 1 is going to transition from something with a DP value of 0. Anything with a DP value of 2 is going to transition with anything from a DP value of 1. Something with 3 is going to transition off of something with 2, and so on and so forth. And so this kind of motivates processing the vertices in increasing order or in these layers depending on the DP value. So base case, when DP is equal to 0, that's pretty straightforward. Any vertices with DP equals 0, their lexicographically minimum path will just have sum of 0. Now let's consider DP of 1. So DP of 1 is going to have some vertices in this layer. They are going to point to stuff in the previous layer. And for each one, we are going to determine, we kind of just look at the outgoing edges, and then we're going to determine, basically, let's say this one has 1, and this one has a 2, and this one has a 1, right? And then DP of 3, or DP of 2, let's say it's going to be something similar, where we have vertices up here, point down to here, and let's say like this one has a 1, this one has a 1, or this one has a 2. I don't know, I'm just making up some values. Say this one has 3, this one has 2, and this one has 1. Now, we don't want to encode each of these as like a sequence of length 2, like 1 and 1, or 2 and 1, or 3 and 2, right? Because that's the whole point. The whole point is trying to avoid that. So what we do is, after processing one of these layers, we reassign each vertex a relative rank within its layer of its sequence. And so here, I'm going to show you an example. So these all have the same relative ranks because they're all nothing. These I'm going to reassign to relative ranks of 1, 1, and 2. So all this means is that this one and this one both have equal sequences, and this one has something that's lexicographically larger. Then in the next one, now we have 1, 1, 2, 1, 3, 2, 2, 1, and 2, 1. Or I think this is I think I wrote a 1 here. So now I'm going to, again, instead of like storing like these as sequences of length 2, I'm going to reassign all of them like ranks. So 1, 1 is the smallest one. So I'm going to reassign this to rank 1. 2, 1 is the next smallest. So I'm going to reassign both of these to 2. And 3, 2 is the largest. So I'm going to reassign this to rank 3. And so now you can see that at each step, I'm always assigning everything inside the layer a relative rank of how it compares to the other vertices within the same layer. And so now when I consider like multiple equal edges coming out of a vertex when trying to recover the path, I don't need to look at the entire sequence. I just need to look at these relative ranks. And if they're the same, then I know they have exactly the same sequence. If they're different, then whichever one's smaller is going to be lexicographically smaller, so I take that sum. And so now I've reduced the work to of computing the sums of lexicographically smallest paths for each vertex to also just n plus m. And so in total, this entire algorithm works in n plus m. All right. So any questions on the second problem? All right. Then we have one more problem to cover. This one was hay bale distribution. So I'll quickly stress this one. So this one is we have n up to 10 to the 5 hay bales. And these hay bales are going to have distinct x coordinates. Or actually, they're not hay bales, they're barns. Or, okay, yeah, I'm just following this. They're actually technically barns, not hay bales. And these are essentially 2 times 10 to the 5. That doesn't really matter. And they're going to be scattered at some integer points, x1, x2, x3. Right? And what I want to do is I want to pick some y coordinate. So they're going to be q queries, q less than equal to 2 times 10 to the 5 queries, where each query is going to give me some a and b. And now, and what I need to do is I need to determine like where should I place like some y so that now if I place a y here, the idea is that this is basically like this is a hay bale distribution site, and it needs to distribute to every barn. And the distribution cost, the cost of distributing to a location is going to be if it's moving to the left. So if it's moving to the left, then it's going to cost a per unit moved. And if it's moving to the right, it's going to cost b per unit moved. And so I want the minimum total cost of like placing this y somewhere to distribute hay bales to all of these barns. Yeah. And we want to do this for each query. Okay. So how can we approach this? Well, we have this cost here. I think it would be good for us to figure out the exact, like write out the exact cost. So the cost function. So let's say we fix y. And also let's fix y. And so after fixing y, let's say there are k barns to the left and n minus k barns to the right. And the cost is going to be, well, it's going to be, for all the ones on the left, it's going to be y minus the x coordinate multiplied by a. So writing it more succinctly, if I pre-compute like prefix sums, it's going to be a times, it should be y times k minus the prefix sum of the first k barns, right? And then for going to the right, it's going to be the sum of all the x coordinates. Each one's going to be subtracted by y. So for the second part of the cost function, it should be y times n minus k, or wait, it should be I'll write on a second line. It should be the sum of all the x coordinates on the right. So I'm going to write this as prefix of n minus prefix of k, and then minus ny times n minus k. So if we know like if we know like how many barns are to the left and how many barns are to the right, then this is the cost function. And so what exactly is this cost function? Well, this cost function is a linear function with respect to y. So it's going to and the slope of this function is going to be a times k minus b times n minus k. So this could be either positive or negative sloped line, but it's going to be some line, like I say this. And if it's a line, then very clearly the minimum of the line is going to be one of the two endpoints, either here or here. So if it's a positive sloped line, if a times k minus b times n minus k is positive, then we should pick y to be the far left endpoint. Otherwise, we should pick y to be the far right endpoint. Now, this is not the full function, right? Because the full function is going to depend on basically if y is here versus here versus here versus here. So like which two, depending on like which bars the y is in between, the k and n minus k are going to change. So the total function overall is going to be a piecewise linear function. It's going to look something like this. On the very end, it's going to look like this, and it's going to look like this, maybe this, this. So this is what the total function is going to look like, right? It's like as we slide to the right, the slope is going to get steeper versus like less steep. And we want to find the global minimum of this function. Now already, if we have a function like this, if we have a convex function like this, we can already apply some techniques like ternary search to find the global minimum. But ternary search on integers is a little bit iffy, and it might be hard to get it to work if they're equal points. And so instead, we can kind of look more closely at this problem, right? It's just like all we want to do is find the line that's like as close to slope 0 as possible, because like slope 0 is like the middle right here, aka where the minimum is. These are slope less than 0, and these are slope greater than 0. And we have the slope, which is just a times k minus b times n minus k. So what we can do is we can just binary search on k to find, I'll say find the first one with a slope greater than or equal to 0. So trying to find this right line. We just binary search for this line. If it's over here, slope is less than 0, we need to increase our bound. If it's over here, we need to decrease our binary search bound. So we're going to binary search for here. And then once we find this line, it's simply plugging into the cost function while picking y to be as far left as possible. And so in total, this is going to be log n per query, or n plus q log n in total. All right. And that concludes this problem. All right. So any questions? Any questions on problem 3 or any of the other problems we covered today? Ooh, let's return to the slides then. Yep, so this is the same chart I showed you before with some of the topics. And so, yeah, the last thing I want to highlight is that we are offering a detailed report card. So basically, if you register with us, you can get back like kind of like a report card, report card that has like pretty much like detailed detailed solutions typed up, and also kind of like what topics you would need to like master in order to like get good at these problems. And yeah, just a lot more detailed information on summarizing this contest. Yeah. And so on the screen here, you see that there's a Google form where you can submit your scores to get back a report card of this report card like this. And also we also have a Discord you can join for more live solution discussion. And I think both of those links have also been sent in the chat. Yeah. Yeah, any questions? Okay, I think that's it then. Yeah. Okay. Oh yeah, thanks for coming, everyone. Yeah.
Hi, everyone. We will open 10 minutes for Q&A section. If you still have question to ask for our coaches and teachers, feel free to stay. Yeah, thanks. We will keep 10 more minutes. Yeah. any question? Yeah, about your USACO problems or anything about you ASCAMP courses, live winter camp, weekend class, small test class, feel free to ask. Max can share all information with you. Max, I have a question. Do you think
Okay.
which problem is the most toughest one?
Oh, yeah, if I had to rank difficulty of the problems, I think it would go, I would say 1, 3, and then 2. So like 1 being easiest and 2 being hardest. Some people might also say 3, 1, 2. But I think yeah, somewhere between 1 and 3, I think are the problems that most people are getting and credit on 2.
Oh, yeah. So which means the problems turns not as the easy, the medium, and then the toughest, right? Not as
Yeah,
this.
I don't think there's a distinct like easy and hardest. I think it's maybe a little bit blending together. Yeah.
So do you have any suggestion for student if they say, okay, the problem one take me so many times, and then do they need to skip the problem one and then go to the next problems?
Yeah, I would definitely not try to like follow some rule like I must solve problem 1 or something. I don't think there's any correlation between uh the number of the problem and how hard it is. And that's definitely proven to be no correlation in history as well. So just like read all the problems. Don't ever waste all your time on one problem, and kind of like look at all your options, and also look at the subtasks too. Yeah, sometimes you don't have to solve. A lot of times you don't have to fully solve the problem to get a good score, right? So also looking at subtasks is worth it if you don't have a full solution.
Okay. So do you have any suggestion for your student like, oh, if I read the problems and like keep coding until 30 minutes or 40 minutes, do I need to skip to the next one? Or do you have any time suggestion for your student?
Yeah, I mean, I guess time is just like, certainly I think if you're in the last hour and you like don't have, if you are in the down to the last hour, let's say, so last hour is like you don't have like much time to code new stuff, you probably just like have time to like finish coding or fixing whatever you already have. I think that's also a good time to start looking at subtasks, like start to look at the other options, see if you can get some partial credit here and there. Um, Also just don't be afraid to try things. Like for problem 2, there were like a number of heuristics. So the hardest part of the problem 2 was comparing the lexicographically minimum sequences, and you can't compare them directly, but there were a number of heuristics that got like a varying number of points, ranging between 14 to 19 test cases out of 20. So definitely don't be afraid to try things if you have nothing better to do, because sometimes you might just get like more credits than expected.
Okay, got it. Yeah, some new participant joined. So here is the Q&A session. Welcome to submit your question or yeah, just open your mic and discuss with our coach and teachers. Because from the parent side, a lot of parents, they are discussing the platinum level rules, right? Because this year the USACO provide a new rules about the platinum. So they are
Oh, yeah.
yeah. Do you think like the gold levels you might be follow the same rules maybe next season?
Oh, I think my guess is, because I think the reason they implemented the rule in platinum is because there were like there have been like cases of people for people cheating in platinum and making like the camp, and then they like don't and then they just don't know anything when they get to the camp. So I think like they might care more about like platinum at the moment and like trying to like stop like cheating or in that division. I think like I think after platinum there might be too many people for them to really care about implementing this rule in other divisions. Because I think in general they want to allow people to have more flexibility to try like every division. That's
Yes.
just my speculation. I don't know really.
Yeah. Because I remember this year, the Dr. Brian Dean also mentioned that every year he needed take a lot of times on develop the methods to solve the treating problems. So that's why the pattern level, maybe the first level to try this.
Maybe,
And
yeah.
to everyone, because this year we still invite Dr. Brandon to come and have the Ask Me Anything events around the midsummer, like June or July. So welcome to stay tuned with our YouTube channel or our social media channel. Yeah, we'll invite Dr. Brandon every year. Everybody, how about this? Maybe you can turn on your mic and share your opinion with our coach. Like, how is your December contest? Is it okay for you? Don't be shy. It's a rare time to have a live discussion with our coach. Okay, so I will just call your name. Do. First. How about Jason? Jason, are you there? Okay, the last student. Zihan, are you there? Zihan, are you there? Okay, Max, thanks. Looks like students are pretty shy, right? I'm not sure why they
Yeah,
would.
I think this concludes the session. Yeah.
Okay, so thanks. We will continue on the silver level. So you need to join Charlie's Zoom, right? Okay.
Yeah, I'll do that.
Okay.
All right. Bye-bye.
Bye. Thanks.